Today we are going to do section 6.2, which is properties of power series on page 544. Now the first thing we can consider is how to combine them. In other words, how to add them together and subtract and multiply by some constant, or even multiply them by some kind of x. So please look at the bottom of the page. Okay, and the addition and subtraction is exactly as how you would expect. That is, to add power series together, all you have to do is just add them term by term, like part 1. To multiply by some kind of a thing, such as bx to the power m, you can pull it right out of the summation symbol. That's because bx to the power m is not a variable in the summation. The variable is n, right? N goes to 0, from 0 to infinity. So anything that has nothing to do with n can be pulled out. So if you have bxm in there, then that's just a common factor. So you can pull that thing out and to become, the whole thing can then converge that way. And then lastly, if you have bxm that's inside n, that still works. It just converges to f of bx to the power m. And everything works. Everything will converge nicely according to the theorem as long as the original series converges to some common interval I. I mean, everything has to converge properly. Otherwise, in the right interval. And because if it doesn't converge, then we have nothing to talk about. But assuming everything converges like it should on the proper interval, on the common proper interval, then everything will work out nicely like that. So that's that. Now to prove theorem 6.2 is quite straightforward. You just use the partial sum. So, and there's a very short proof here in the book that so please do that proof, which is only for part 1, which is this addition. Please do the proof as part of your homework. So next, let's look at example 6.2. The example 6.2 is now we are applying the theorem. Now, being that the theorem is very straightforward, right? There's not much to it. Applying it is even more straightforward. You just do as you're told, add the terms together, and then you get your answers right away. Well, I'm not able to close. What's wrong? Okay, I'm not able to flip the page. Come on. Okay, there we go. So then that's the example, and that should come out right away. So please do that example as well for your homework, example 6.4. Next, let's look at example 6.5 on the following page. This example is something we have done at least a couple of times by now. That is, if you are giving some kind of a fraction or fraction-like thing, or a rational function, you need to beat it and use the power series rules to beat it into an infinite series. As we've done that in previous homework, so this is no different. So please do example 6.5 as part of your homework. And you might also be concerned with the interval of convergence, which is fine. You just check to see if it converges or not. That's that's about it. So please do example 6.5 as part of your homework. Next, example 6.6 on page 547. We have, now we're doing the opposite. You're giving some kind of a simple power series, and you want to use the geometric series to beat it back into a rational function. So yeah, you just plug it in, and out it comes. Okay, so do that one also as part of your homework, please. Now next, example 6.7, I'm going to skip that because it talks about winning the lottery, and then you'll be paid $1 million a year forever. And I mean forever, unto eternity. I have never heard of such a thing, so so I'm going to skip it. Okay, feel free to read it yourself, of course. I mean, yeah, somebody's going to pay you $1 million forever. Let's anyway, so let's flip the page. And next, I'm on page 550. And let's look at how to multiply power series. Okay, so that's more interesting. How would you multiply power series? Now, normally when you multiply two polynomials together, you multiply each term with every other term, right? And power series is no different. So let me write this down. So I have written down two sample random power series that I made up in order so that we can multiply it together. Well, this goes to infinity. Okay, this goes on. So that's this one, which is your book. Write it as like this, right? There's a Cn, which is the top one. Cn x to the power n, the sum. And then the other one is the dn's x to the power n. But I'm going to use a real example without all the too many CNs and DNs to show you how the multiplication is done. What you're going to do is multiply each one by every single one at the end. Now that sounds like something that will take forever, right? Literally. But we're not going to do it that way. Actually, what we're going to do is simply calculate the coefficients of each item. First, we'll calculate the final result, just the numbers. Okay, just the numbers is of course the first one. We multiply only numbers where x is power to x to the power 0. Then the coefficient is just 1. Okay, and then x to the power 1. What becomes x to the power 1? We have to multiply this times that and that times that, right? So then the next one should be 2. So the next term will be 2x. Okay, and then and that's all the stuff that will ever become 2x. Okay, now nothing else is gonna have x to the power 1 because everything else has more power than 1. And the next term, same thing. How we'll collect everything that will create x to the power 2. What will become x to the power 2? Well, the 1 times x squared. Okay, so 1 plus, and then 1 times x squared, and then x times x, that's 1, and then 1 times x squared over 2. And I believe that's about it. There is no other way to get x squared out of it, right? Is there any other way? I don't think so. This is about it. So we have, so this is like 2.5, okay? X squared. That would be the coefficient for x squared. And you continue doing this, and as you can see, as you go on, you have more stuff to add and get very quickly. But I'm tired now, and I'm going to stop right here. So the infinite multiplication, we'll do maybe 3 of them and then call it done. And that is what your book is trying to say. See, to multiply those things together, you will multiply them according to the power of x. See, you do C0 D0, then C1 D0 plus C0 D1. That's for x. And then blah, blah, blah for x squared. And then you keep going. But in practice, when we multiply stuff infinitely, we do maybe 3, and then we're 1 out. So we don't do it anymore. Okay? So that is the idea of how to multiply a power series. Now we have done that, and let's flip to the next page on 551, where we has a theorem that talks about multiplying power series. And the way to multiply it is if you have two series that converges properly on a common interval I, then you can totally multiply stuff like I said, okay? And the resulting infinite power series will converge properly and make sense and all that. Now, I don't know if this thing converges. It might not, or it might if you have a small enough interval, whatever. The point is, if they converge, that your two power series converge, then when you multiply them together, they will converge on the same level that the previous two power series, the same interval. Okay, that the other converges. That is, everything will work out nicely as long as you start out in a nice condition that everything is converging on the common interval. All right. So having said that, the next job, example 6.8, we have to multiply the power series with some other thing, and then you're gonna pull out some power series, which is which you please do that as your part of your homework. Very similar to this. And of course, you're not going to be multiplying stuff forever. You're only going to do maybe 3. Oh, the book went all the way to 5 terms. Yeah, well, do that. Okay, so that's example 6.8 on page 561. Next, let's talk about differentiating and integrating power series. You have some power series like that. We're going to differentiate or integrate it. Now that sounds, I don't know, sounds impossible. I mean, this thing's infinite. How are you going to do that? Actually, it's very simple. Okay, in fact, that is a huge benefit of power series, is that you're going to differentiate or integrate it as if it's a polynomial. It is a polynomial, except that it's infinite. Polynomial in the sense that it just have a bunch of x's with with integral powers like that. See, so you differentiate it exactly that way, or integrate. Same principle. If you integrate exactly as if it's a polynomial, one term at a time. So let's look at the next page, Theorem 6.4, where it says that if your power series converges properly, right, in some kind of a radius of convergence or some interval that's open, we're not considering the endpoints. The endpoints, as you know, might or might not converge, so we won't worry about them for now. But let's say it converges in some interval. If that is the case, then you can take the derivative of the power series by taking the derivative of every single thing, okay? Or you can integrate it the same way, and then after you integrate, you're going to have to add a constant. Now, if you do that, then the resulting different derivative or integral will converge properly on the same interval as you started. So very nice. Okay. Now the way to say it, of course, is as your book has shown very nicely, that here's the original function, right? And then a power series, and you take the derivative, and which becomes nx to the power n minus 1. Okay, and then integral becomes n plus x to the power n plus 1 over n plus 1 plus your constant. Don't forget the constant for the indefinite integral. And then that's about that. So you just so the very tough situation turns out to be actually made easy, because the infinite series has that unusual benefit. Now we're not going to prove the theorem because the proof is not included here, so we'll ignore that just like the book does. And then look at the example 6.9, which is to differentiate some power series. So please, again, you just do the same old differentiation of polynomials. So please do example 6.9 as part of your homework. And then next, example 6.10, same thing. We need to integrate this thing. You integrate it, well, piece by piece, one at a time, which is a very straightforward integration. And then you add it up, and then it comes up with something. Now, remember that we don't know anything about the endpoints usually. Sometimes they might converge, sometimes they might not. Just remember that the endpoints are not guaranteed. So that is, let's see, what is this? Right. So that is example 6.10. Please also do that as part of your homework. And finally, we have come to Theorem 6.5, which is the uniqueness of the power series. Well, are they unique? The proof of the uniqueness, first I should say the uniqueness means if you have a function that is represented by two different power series, then those two different power series has to be completely identical, term by term identical. Okay, you cannot have two that look different. They have to be identical. That is, every single coefficient will be the same. Now, how would you prove that? What you do is that you describe two power series, and then you subtract them. I believe, yes, you subtract them, and then take the derivative of them. Okay, and then they're forced to become 0. So the proof is very short. So please prove the uniqueness of power series as part of your homework. Okay, so now we have come to the end of this section for homework. On page 558, please do problems 63, 67, For problem 67, I'm positive that the answer of the book is wrong. Well, for one thing, it doesn't even make any sense. Okay, and but it's not very wrong. I think it's more like a typo. But anyway, next 71, 79, 83, 87, 89, 91, 95, 99, 105, and 109. And when you finish your homework, come back and I want to talk about them. Now that you have finished your homework, I want to talk about it. First, I want to talk about problem, what is that? Give me a second, I'm missing something. So let's look at problem 67 first, which I forgot before. Now the problem 67, we have some kind of a fraction, and we're supposed to beat it into a geometric series, power series, by using the geometric series formula. So first, when you see something like that, you're going to break it, okay? Use the partial fractions calculator. However, when you do that, do not input x squared, just input x, okay? Use x for x squared, and then plug x squared into it when you see the result. Or you can do it by hand, of course. Now, once you have done that, then you force each one into the geometric series, right, like this, and then eventually add up to be some kind of a result. Now, the answer at the book back is somewhat different, but I'm positive this is correct because the answer at the back isn't even consistent. So then, yeah. So, but if you get the if you get the same answer as me, then you should be right. I mean, that also proves that I'm right. If you get the answer at the back of the book, then I might be wrong. But I did look at it for a long time and made sure that I am right and that the answer at the back is wrong. But anyway, so that's just a simple matter of beating a fraction into an infinite series that we have done several times already. So next, let's look at problem 71, which is what is that? Oh, it's an infinite series that we're going to beat it back into a fraction. So we're going to follow the rules. Okay, the rule is, here's the geometric series. The geometric series comes in two forms. Either n start at 1, okay, which your coefficient, it has to be r to the power n minus 1, or the other one, n start at 0, when then r is just n. The two are identical. It's just how you basically how you count it. Okay, whether you start counting at n equal to 1 or n equal to 0. Now, in this case, 71, I'm going to start at n equal to 1. And, well, because they did. Okay, so I'll use this formula. First, I did something and it screwed up, and so I had to do it again. So let's see the right part. The right part to fit this thing into this exact formula where r is x minus 3. So I have to pull another x minus 3 out so that the coefficient comes out right. Yeah, to be exactly. So then if you do some algebra, so then the power is exactly n minus 1. So that is exactly the same as the formula over here, see? So then once that's done, then you follow the formula and then come up with the right answer, and that is correct. So next, let's look at problem 79. This one, we're supposed to turn the infinite series into the fraction with the help of the geometric series. This one, the trick is to break this into 3 different series that looks like that, right? You have the 3k minus 2 series, all plus, 3k minus 1, also all plus, counting from 1 to infinity, both. And then the 3k ones are minus. See, every third one is minus. So you do it this way, and then rearrange everything so that it looks exactly like being that we're starting to count at 1. We use this formula, okay? And you have to make the r to the power n minus 1. So when it is 3k minus 3, you pull the 3, you factor out the 3, it becomes x cubed or something, and then you rearrange it, and this is the result. All right, so yeah, at least I believe that's the result. Let me look at it a little more to make sure. Yeah, it's right. All right, and I also checked with the back of the book. So let's look at the next problem where we have 83. What are we doing? Oh, I think multiplying two two infinite series. So you multiply as you are told. You multiply all the constants, then all the coefficients that has x to the power 1, then everything to the x to the power 2, and so on and so forth. When you are done, you get something like you end up with something like this, okay, right here, where you have the sum of n goes from 0 to infinity times xn. When that happens, you can use this. There's a summation formula on page 8 of your book, which turns it. This sum is exactly this formula right here, okay, with the 2 not canceled. I canceled the 2 because there was a 2 here earlier, and then that comes out to be the right answer. Yeah. So that's that. Next, let's look at problem 95, where you have the function is natural log of x, and you're supposed to come up with the infinite series for it. And the way you're going to do it is by somehow pulling a trick and make it look like the geometric series. Now, the natural log doesn't look anything like the geometric series. However, is integral or derivative or something does. So that's what we're going to do. First, we'll follow the book's trick that says we'll write 1 over x in this form. Why we're writing it in this form? Because then we'll use it, apply the geometric series, okay? This time we'll start at 0. See, up here, because that's what the book wants us to do. So we'll start at 0 and beat this thing into a geometric series. But that's still just 1 over x. And what about natural log? So we'll integrate 1 over x, which is the natural log, and then we integrate the entire series. Like it says, we'll integrate it term by term, which becomes x minus 1 to the power n plus 1 divided by n plus 1 by the power rule of integration, and so on. And then we establish that the constant is just 0 in this case, and therefore that is the answer to the natural log in representing the natural log in the power series situation. And that's the end of the problem. Next, let's look at problem 99, where f of x is tangent inverse x squared, which is fine. Now, by rule 16 of your derivative rules, the derivative of tangent inverse is 1 over 1 plus x squared. In case you forget, that's on page 700. Now that we know that, let's do that. Okay, so we take the derivative, which don't forget the chain rule. I actually forgot the chain rule the first time I did this, and I couldn't get the right answer. I wonder why. So by applying the chain rule, you have to plug x squared where x is. Okay, x squared is now the new x, so you have to plug x squared right in there and then square it again, and then take the derivative of the inside, which is 2x. So then it equals to something, and then you turn, I guess then you use that and turn it into the power series, the geometric series formula. And that is right. And after that, you get some series, and then we're going to integrate this thing. Why? Because we took the derivative, but we need to know what the original is, right, in terms of power series. So we found the derivative of the series. So we integrated to get the original. And once you do the integration, you get it to be something like this. And yeah, and that's about it. And then, of course, the constant, when you integrate, you have to worry about the constant. But in this case, the constant, the tangent of 0 is 0, so the constant is, you can ignore it. So then the tangent inverse is equal to that thing. And that is correct. Now I have, then I look at the back of the book, and the back of the book did it differently. Well, it's actually the same process, but it looks different. So, and also, while my process is what we would normally do, the back of the book used the fundamental theorem of calculus, which we also did, but we didn't exactly go by the definition of it. So I wrote down how the back of the book did it because it's more elegant this way. Okay, it does look better, but we haven't directly touched the fundamental theorem of calculus for a while. Now, by the fundamental theorem of calculus, the tangent inverse of x squared is defined by the integral from 0 to x squared of 1 over 1 plus t squared dt. And that, how do they know that? It's because of the rule 16. Like I said, same thing, but looks different, right? So then, so that's true by the fundamental theorem of calculus. So then if that is true, then next we're going to turn this thing, I mean the integrand right there, 1 over this thing, which looks like the geometric series format, and it is. So you turn it into the geometric series, and then you integrate it, okay? And then you evaluate it from 0 to x squared, and when you're done, you come out with the exact same answer we came up with earlier. But it does look better and neater, and plus it reminds us of the fundamental theorem of calculus. So I thought that was worth mentioning. And that is the end of 99. And one more problem I want to talk about, 105, which is all right, which is this thing. And this series looks weird, okay? I mean, it's not like what we've been doing, because there's a k on top and k on the bottom. I mean, the k on top is in the power. We can handle that. The k on the bottom is harder to figure out how we're going to get rid of it, because without getting rid of it, we can't apply the geometric series principle, because there's a variable down there, right? Because k is going up from 1 to infinity. So what we're going to do, so the first thought I had was to take the derivative of it right here. So I took the derivative of this function, assuming everything converges properly and all that stuff. And then I come up with, so by taking the derivative of this thing, I got rid of the k on the bottom, okay? And once that's gotten rid of, then I just manipulate it into a geometric series situation and got the answer right here. Now, when I got the answer, that's only the derivative. What's the function itself? Then on this side, I have to then integrate what I got, right? I got this, but I have to integrate it to get what the original function is. And the original function turns out to be this thing, with the constant being 0. And that is the right answer, I hope. Let me I'm sure I checked the answer. Yes, I did check, and it is correct. Moreover, the x converges for when x is less than 1, okay? Being that it's a geometric series. Geometric series converges when it's less than 1 and diverges when it's bigger than 1. And so that's the radius of convergence. And with that, we mark the end of this section.